Alright, today we're doing a Bitcoin mining deep dive. Last time we talked about the basics, and next time I will explain to you why Bitcoin mining is so complicated. But now a quick recap. Last time we figured out that Bitcoin mining is done by computers, and that it basically means that they finalize the new transactions into a block. But what does mining actually mean, and how does it work? Today we will look at this, and to do that we first need to do a quick computer science crash course, because to understand mining you need to know how computers work. And basically what it all comes down to is this thing here, which is a transistor. And this is what a transistor looks like if you buy a single one, and this is the schematics of it. And basically a transistor has 3 in or outputs, or 3 legs, and it is just an electronic switch. So unlike a mechanical switch where you have to use your finger to turn it on and off, an electronic switch can be turned on or off by applying a voltage to the base, which is usually the middle leg. And so if you apply a voltage to the base, electricity will flow from the collector through the transistor and out the emitter. And let's say if you had LED here, it would be turned on. So by applying a voltage here, electricity can flow through the transistor and turn something on. And the same for the scenario where you put base to ground, or you apply 0 voltage to the base, then the transistor stops conducting electricity and the LED would be turned off. And so just like a mechanical switch, a transistor has basically 2 states. It can be off or on. It can conduct electricity or not. And the lamp would be on or off. And basically everything in computer science, your whole CPU, the RAM, everything, it is all based on a complicated build-up of billions of these tiny little electronic switches, which is why everything inside your computer has to be a representation of zeros and ones, because it is all based upon these tiny little switches being on or off. And so if you type, for example, capital A on your computer does not know what a capital A is. And so internally in your CPU or in your RAM, the computer needs to represent this capital A as a sequence of zeros and ones. And this whole thing here is the ASCII table, where every character in the alphabet is represented or mapped to a sequence of ones and zeros. And specifically, it's an 8-bit sequence, because every 1 or 0 in this sequence is called a bit. 4 bits are a nibble, and 8 bits are a byte. And so if you type capital A in your computer, what is stored in the RAM is 0100 0001. Alright. Now the same thing also applies to numbers. We humans use the decimal system, and so 56 in decimal has to be somehow understood by the computer. But the computer, as I said before, only understands 0 or 1. because it's a giant machine built of tiny electronic switches that can only be on or off. And so we also need a mapping from numbers to sequences of ones and zeros. And so the decimal system comes from deca, meaning 10, because every position in a number has 10 digits. It can be 0, 1, 2, up to 9. And binary comes from the fact that it has only 2 possible digits per positions, 0 or 1. The same way that the number 56 is based upon 10 combinations per position, the binary system is based on 2 combinations per position. And so the first position in a decimal number is basically just the digit times 10 to the power of 0, which is 1. And so if we have 5 at the first position, it's 5 times 10 to the power of 0, which is 5. And for the second position, every time we increase the digit in this position, we basically add 10 to the value of the number, because it has 10 digits or 10 possibilities that were increased before the digit was increased at the second position. And so the second position is always the digit times 10, which is 10 to the power of 1. And in this case, this would be 60. And if we had a third position, it would be the value of that digit times 100. Because it would be 10 times 10, 100. And so every time you increase the value in the third position, you increase the value of the total number by 100. For 56 this is not the case, and so we have 5 times 60 is 65. And so in the binary system you only have 2 possible digits per position in the number. And so with just 1 bit you can only count to 1. And then if you increase the second position to 1, you have the value 2. If 0, 1 and 1, 0 would be 2. Then 1, 1 would be 3. And then to count to 4, you need to increase the third position from 0 to 1. And so every time you increase the position in a binary number, you add a factor of 2. So the first position allows you to count to 1, the next allows you to count to 2, then to 4, to 8, 16, 32, 64, 128. So the same way we multiplied by 10 to the power of the position, we now multiply the digit value by 2 to the power of the position. So at position 0 it's 2 to the power of 0, which is 1, so you have 1 times 1, which is equal to 1. Then you have a lot of zeros, and then at this position number 6, right, it's like 1, 2, 4, 6, 8, 16, 32, 64. And so this 1 times 2 to the power of 6 would be 64, and together this also results in 65. And so we've shown that 56 in decimal is the same as this sequence in binary. And now, to make things even more complicated, we add the hexadecimal system, where you have 16 possible digits. So just like the decimal system, you have the digits 0 to 9, but then if you would have 10 in decimal, you would write A in hexadecimal, and 11 would be B, and so forth until 15, which is F. And this is a very computer science specific number system, because it allows you to just summarize 4 bits as one number. And so 56 in decimal is the sequence in binary, and in hexadecimal you just always take 4 bits and convert this number into the hexadecimal system. And the first 4 bits would be just 1, and the other 4 bits would be 0 times 1, 0 times 2, 1 times 4, and 0 times 8, which is 4. And so in hexadecimal, 56 would be 41. And again, down here in the ASCII table, you can now see that internally this sequence can be either used to represent a number or a character. And if you want to, you can also just look at it as a different number in the hexadecimal system. Now this might seem a bit complicated, but the main takeaway here for you is that we now understand that all the information that a miner, or any computer for that matter, stores internally for such a block is basically just a giant sequence of ones and zeros. Because everything inside your computer is a combination of ones and zeros. And what the miners now do is that they can take this sequence and they can put it into a hash function, which is a well-defined protocol of how you can convert any sequence of ones and zeros into a specified length output. And for the hash function that Bitcoin uses, the SHA-256 algorithm is used, and this algorithm always outputs a sequence of 256 bits. And since we now display the output here in hexadecimal, every digit that you see represents 4 bits, and so the output here is 64 digits long, representing 256 bits. The important thing for now is that these hash functions have certain very important and consequential properties. And the first one is that the same input will result in the same output. And so every time you use this exact block, which is internally in the computer, just this sequence of zeros and ones, every time you put this sequence into the SHA-256 hash function, you will always get this exact output, which means that everyone in the Bitcoin network can use this information, put it into the SHA-256 algorithm, and get the same output. And this is important because then everyone can verify that this output is the one that is correct. And then the next important property of hash functions is that a slight change in the input will result in a completely different output. So for example, if you only switched this 0 here into a 1 in the whole sequence, right? Maybe you convert this capital S in store to a small s. Then you get a completely different output sequence, because the SHA-256 hash function basically just chops this sequence up and mixes it up until you get a 256 byte output. And so just changing one single bit will result in a completely different output. And this has important consequences, because this is the reason why the miners only need to adjust the nonce, this one special number that you've probably heard of. They don't need to change anything here, they can only change this number to get a very different output every time they put this data into the hash function. And now if we combine this with the third property of the hash function, which is that there is no way of inferring the input from the output, meaning that the hash function is basically a one-way street. You can always put in a certain sequence and get a certain output, but there is no way of figuring out what was put inside the hash function if you only have the output sequence. This means that the miners have no way of predicting which output sequence they will get if they put a random sequence in, right? Because if they just change one bit, it will be completely different, and since they have no way of inferring which input resulted in which output, all they can do is basically just change the nonce, put the sequence into the hash function, and look at the output function. They cannot say, oh okay, now I have like 5 zeros here, but I want 6, and so I need to increase the nonce by 10. They cannot do that. They can just change the nonce and try again and check if the output has a certain number of zeros. Now, why do they need to check the number of zeros and the number of leading zeros, to be specific? Well, that's because Bitcoin has a mechanism where every node only accepts a new block if the output of the hash function has a certain number of zeros. Again, why this is the case and why it makes sense to have something so complicated will be looked at in the next video. But for now, just know that this is a very important mechanism in Bitcoin, and this is why the miners need to take the transaction data, guess a random number, put it into the SHA-256 hash function, and then check the output sequence if it has enough leading zeros. And if this is the case, they can publish their block with the special number, the nonce, to the network, and everyone in the network can use the same SHA-256 hash function and calculate the same output value and verify themselves if this output sequence has enough leading zeros. And if this is true, then they too will agree that this block is correct, and they will add all the transactions to their ledger, which means that now everyone in the network agrees that these transactions are valid, and that, for example, miner XY now has 3.125 Bitcoin to spend. Alright, I hope this was somewhat logical and you were able to follow, feel free to watch the video again, because it's a bit intimidating at first and you might need to watch it twice or maybe even 3 times. But while we're still at it, let's also look at the difficulty adjustment. And the difficulty adjustment is another mechanism in Bitcoin that makes sure that on average a new block is mined every 10 minutes, right? Because if a lot of new miners come online and they also start guessing, and sometimes they guess billions or gazillions of new nonces per second, then you would think that they would find new blocks faster and faster. But this is why Bitcoin has the difficulty adjustment, which means that all the nodes in the network, they always calculate the time it took between the last block and the newest one, and then they take the average time between these blocks of the last 2016 blocks, which is about 2 weeks at 10 minutes per block. And if the average time that it took to mine these 2016 blocks is below 2 weeks or below 10 minutes on average, then they will simply reject all the blocks that have only the current number of leading zeros. So they will demand that a new block has more leading zeros. And the more leading zeros that are needed, the harder it is to find a block that has this number of leading zeros. Because of the property of the hash function, that it is impossible to predict the output, every hash function calculation is basically a random outcome. And so every bit out here, or if we look at it in hexadecimal, every digit here represents 4 bits. Every outcome is basically a random outcome. And so think of it like a coin flip. If you want to have 1 head, that's a 50% chance of getting 1 head. If you want to get 2 heads in a row, you have a 25% chance of getting 2 heads in a row. But then if you want to get 3 heads, that's another 50% reduction, so 12.5%. And if you want to get 4 heads, that's 6.75% chance. So every zero here represents 4 bits, which is basically 4 coin flips. And so just to get a 0, which is 4 zeros, 4 bits as a 0, you have 6.75% chance to get a 0 at the first position. And the more zeros you want, the more leading zeros you want in your final output, the harder it is to guess a nonce that will result in this output. And so by increasing or decreasing the number of zeros that are required for a valid block, this way the network can keep the average at 10 minutes per block. Because if new computers come online, it will just become harder to mine a new block. And so even if more guesses are made per second, if it's harder to guess the right number, the average will become 10 minutes again. Alright, feel free to watch the video again and again until you understand what I explained to you today. And next time I will also explain to you why Bitcoin has all these complicated mechanisms like the difficulty adjustment, and why we need to mine Bitcoins in such a complicated way. So I hope you learned something, and see you next time.